Welcome everyone to the HSC Physics April 8 Notes lectures presented to you by, of course, 8 Notes. So a little bit about myself. My name is Thamika. I'll be your lecturer today. So I graduated from North Sydney Boys in 2022 with an ATAR of 99.30. In university, I'm studying medicine all the way in Queensland, and some of my hobbies are, well, I'm going to be honest, I picked up two of these hobbies after the HSC, so Bed Wars and Valorant. I started playing that a lot after my HSC, and I've been playing piano for a while, and I enjoy that quite a bit. So yeah, that's a little bit about myself. And now a quick bit about ATAR Notes. So since 2007, we've been offering heaps of free resources to make sure students just like you can thrive in their studies. And we've offered free lectures like these ones since 2015. These free lectures are in line with the ATAR Notes mission to help students as much as possible, and we have tons of free resources for you. So looking at this slide, here are just some of the things that we offer. And if you want to find more, you can go to atarnotes.com. So if you want to find more info on tips on how to use these resources, check out the info doc under the resources section of this page. We have free notes, free videos, and free guides made by past students. And if you have any questions after the lecture, the best place to go is to the Q&A section where either current or past students can answer your questions. I'd like to thank all of our sponsors and partners on this slide for allowing us to make these lectures possible. And with that said, let's get right into the lecture. So this lecture, which is going to be on module 7, it's a pretty chunky module, that's what I got to say. And what we're going to be studying today, it's not exactly in syllabus order, but most of the stuff that you will cover in the syllabus will be in this lecture. So we're going to be doing it in two separate parts. So the first one is going to be on the electromagnetic spectrum, the wave model of light, and the quantum model of light. So in that subheading, we'll have the development of the model of light. So I like to think of this as a story. So we're following the story of the development of light and also the development of physics along with that. So Module 7 and Module 8 are very much like a story. So you follow the story of the atom and you also follow the story of light. So for this module, we're going to be following the story of light. And we'll also be learning about wave behaviors and black body radiation as well, which kind of like allows us to segue pretty neatly into the second block, which is the quantum model of light, special relativity, and Einstein's gigabrain. So yeah, he was pretty smart. He like invented a whole new like subsection of physics and stuff. So yeah. In this second block, we're going to be doing the photoelectric effect, spectral analysis, Einstein's postulates, and energy mass equivalence, so E equals mc squared. A few more things. So the words in red, you'll see these like throughout the slide. So the red words are keywords, and you should be able to either define or like explain what they mean. And another disclaimer is that this is a whole module in 2 hours. So it's okay to not understand every single detail right now. The purpose of this lecture is to give you a foundation and general understanding so that learning later will be a lot easier for you. And with that said, let's get right into it. So we all know now that light is an electromagnetic wave, and you can see here that electromagnetic wave is in red, so you should be able to define it later on. We know now that light is an electromagnetic wave, but what exactly is an electromagnetic wave? How would we define it? So an EM wave, or an electromagnetic wave, is a wave consisting of electric and magnetic fields oscillating at right angles to one another, which can self-propagate through empty space. So that is a good definition for an electromagnetic wave. And the key words that you need to remember here is EM waves can self-propagate. So they can self-propagate at one another, and they have electric and magnetic fields oscillating at right angles to one another. So that's the important part here. So let's unpack what we mean by self-propagation. So these Gauss's law, Ampere's law, Faraday's law, we'll learn a bit about them later. Like, you don't need to know too much about them. You just need to know how the process of self-propagation occurs. So a point charge produces an electric field. I'm sure many of you will know that. This is following Gauss's law, but a lot of people will know, like not knowing Gauss's law will know that a point charge will produce an electric field. An accelerating point charge then produces an electric field as well, but a changing electric field this time. And now following Ampere's law, a changing electric field produces a changing magnetic field. And a changing magnetic field following Faraday's law will produce a changing electric field. So what happens is these two cycles like keep repeating one another. So the changing magnetic field here produces a changing electric field, and then this changing electric field produces a changing magnetic field, which produces a changing electric field, and so on and so on. So these last two steps, they keep repeating one another, and so the EM wave creates itself. So the EM wave is now self-propagating. So that's how that process of self-propagation occurs. So yeah, Looking at the electromagnetic spectrum now, a bit of a recap. Basically, we have radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. And as you can see, the wavelength decreases as this keeps going and the frequency increases. So the energy it carries increases. So yeah, that's a quick little recap of the EM spectrum. So now we can talk about James Maxwell. So electromagnetic waves were first predicted by James Maxwell. So you can see his name is in red, so we do need to know a little bit about him. So what he did was he put together the four equations to unify electricity and magnetism. So he unified the laws of electricity and magnetism to create electromagnetism. So if we go back now, these Gauss's law, Ampere's law, Faraday's law, those were all like the laws that he unified to create electricity and magnetism for the first time. And what he did was he described EM waves as self-propagating waves with electric and magnetic fields oscillating at right angles to one another. So he gave us this modern definition of EM waves that you will be using. And the final thing that he did was he also rearranged the equations to predict that EM waves should travel at a speed given by, you can see over here, 1 over root 2 constants multiplied by one another, which gives us an approximate speed of 3 times 10 to the 8 meters per second. And if we now think about the speed of light that we already know, we see that the speed of light that we already know is approximately also 3 times 10 to the 8 meters per second. So yeah, now let's go through a NASA sample question. So James Clerk Maxwell made significant contributions to physics. Which of the following did Maxwell not contribute to our understanding of physics? Let's go through this. Did he predict the velocity of electromagnetic waves? Well, yes, he did. He rearranged the equations to predict that EM waves should travel at a speed given by 3 times 10 to the 8 meters per second. So he did do A, and so he did contribute that to our understanding of physics. Question B now. Did he predict the existence of electromagnetic waves? Let's go back. These electromagnetic waves were first predicted by James Maxwell. So he did. He was the first to predict the existence of electromagnetic waves. Now let's go to C. Validating the existence of electromagnetic waves. Did he validate the existence of electromagnetic waves? As in, did he conduct experiments to prove that they existed? Well, the answer to that is no. He only predicted the existence of electromagnetic waves, but he never conducted experiments to prove that they existed. Or he was unable to prove that they existed. He never did. So he did not contribute to understanding of physics. So in this case, the answer would be C. So now let's look at D. Unifying electricity and magnetism through equations. So he did do that as well. He put together the four equations to unify electricity and magnetism for the first time. So A, B, and D, he contributed to our understanding of physics. C, he did not. So the answer in this case is C. So now let's look at how the speed of light has been measured. So the speed of light has been measured many, many times by various people over the years. And the first ones that were used were quite inaccurate, but it did get more and more accurate as time progressed. So the first one that you'll be learning about is Galileo. So his method was pretty goofy. So he got himself, so I'll say Galileo's G and participant 1 is P. So there's G and P, right? So G stood on one mountain and P stood on another mountain of similar heights, right? The distance between G and P, or the distance between the peaks of those two mountains, was approximately 10 kilometers, let's say, right? And G had a clock, or a stopwatch, or whatever stopwatch they had in their time, and a lamp. P had just a lamp. So what he did was G would start the stopwatch and his lamp on at the same time, and he would wait for that light to travel from his lamp approximately 10 kilometers to P, and then he would wait till P saw that G's lamp turned on, and then P would also turn his lamp on, and then so the light would travel from P's lamp to Galileo's eyes, or G's eyes, and then G would stop the timer when G saw P's lamp turn on. So yeah, it's a little bit confusing to explain verbally, but if you think about it, what he's trying to measure is he's trying to measure the time it takes for light to travel 20 kilometers. So let's say the gap between G and P is 10 kilometers, or the gap between the two mountains are 10 kilometers. Galileo is trying to time the time it takes for light to travel 20 kilometers. So there are a couple of things that are glaring limitations of this model, glaring inaccuracies that might happen in this model. So it's a common knowledge that in 1 second, light will travel 7 times across the Earth. So yeah, in 1 second, light will travel around the globe 7 times. So think about that. And now Galileo is trying to find the time it would take for light to travel 20 kilometers. So human reaction speed is a big source of error in this experiment. And well, basically human reaction speed is going to be like slower than the time it actually takes for light to like travel between Galileo and P and back to Galileo. So yeah, it was really inaccurate. So what happened was Galileo ended up saying that light was like 10 times faster than the speed of sound or something like that, something really goofy like that. And so yeah, he did conduct an experiment. So this was a historical means of trying to find the speed of light, a historical experiment conducted to find the speed of light, but it was quite inaccurate. So also just like, heads up, in terms of the questions that you can get for these types of questions, they can ask you to compare between a historical and modern means of finding the speed of light, or they can ask you to in detail describe like how people describe a historical means of measuring the speed of light. And if they ask you to in detail describe, for example, using a 5 marker, for example, a good tip is to always draw a diagram. So you always want to end up drawing a diagram. So for example, in this case, for Galileo, you'd end up drawing 2 mountains and one dude on one mountain, one dude on the other mountain holding a lamp, for example. So yeah, you always want to draw a diagram if it's above 5 marks and they're asking you to detail Galileo's methods of describing the speed of light. And another thing is they might ask you to describe the limitations of each models of light. So that's also something that you want to look out for when you're going to be restudying this module. So the next person we're going to be talking about is Romer. So what Romer did was he used the orbit of one of Jupiter's moons to find the speed of light. And his method was pretty decent. He got pretty close, a lot closer than Galileo. And then we have Fizeau. So Fizeau used a pretty clever setup involving a rotating cogwheel, and he got really, really accurate to the speed of light. So what he did was, so we have a cogwheel, right? And this cogwheel has teeth and it has a gap between the teeth, right? What he did was he had a light source and a mirror, pretty far away, let's say 10 kilometers again. And he turned on the light and waited so that one light beam would travel. So let's take one light beam. That light beam would travel through the gap of between the teeth in the cogwheel. So he traveled through the gap, hit the mirror, come back, and he'd turn the wheel so that by the time that light wave came back, it would hit the teeth instead of the gap. And so that light would be blocked out. And so he'd rotate the wheel fast enough so that every single light wave that was sent out by the lamp would get blocked out. And so he knew the distance that light traveled, and he knew the rotational velocity of the cogwheel, and he knew the time that he knew the rotational velocity of the cogwheel. And using this, he would be able to find the time that light took to travel that distance that is known. And using that, he could find the velocity of light. So that's kind of the method. It's a bit confusing to understand verbally, but that's kind of the method that Fizeau used, and he got a pretty close value to the actual speed of light, or the accepted speed of light that we use nowadays. After Fizeau, there were a couple people after that. So there was Foucault, but now in the modern means of measuring the speed of light, we use lasers and superposition to find the speed of light. So now we get pretty accurate, a lot accurate than these guys. But with what they had, Fizeau was quite close, and he had a very clever setup. So yeah, a bit before this, so James Maxwell, we did mention before that he didn't validate the existence of electromagnetic waves. So there was an experiment conducted, or there was someone who experimentally found evidence towards the existence of electromagnetic waves, and his name was Heinrich Hertz. And if you want to look up Heinrich Hertz spark experiment, you can find out that he found out that electromagnetic waves actually existed. So that was what Heinrich Hertz contributed to our understanding of physics. So now let's go on to the development of the light model. So this is where the story begins. So let's take this as chapter 1. So chapter 1, there was a lot of debating or doubt in terms of whether light was actually a particle or whether it was a wave. And so two guys spearheaded this argument. So one was Newton, who believed that light was a particle, and he called this particle corpuscles. And then there was Huygens. So Huygens believed that light was a wave. And so these guys were battling it out, trying to see who would trying to prove to the other person whether light was a wave or a particle. And basically, both models were pretty effective because both models were able to explain basic properties of light. So light could reflect, light could refract, light could diffract. So these standard properties, both models were able to explain. But what they couldn't explain was the polarization of light and the interference of light particles, or light itself. So those could only be explained by the wave model of light. And so because of this, the wave model of light took precedence, and the wave model of light became more accepted. In terms of the red over here, so corpuscles are like, the light particles or particles of light that Newton believed light were made out of. Reflection, refraction, diffraction, you should be able to either detail or visualize what those look like. And polarization and interference, we'll go through that in a bit. So yeah, because the wave model could explain polarization and interference and the corpuscular model couldn't, the wave model was more accepted, or people saw the wave model as more of a reality. And also they conducted experimental evidence that showed that, so basically Newton believed that these corpuscles, these particles, were attracted to matter basically. And so if it entered a more dense medium, so if it went from air to water, for example, these corpuscles would speed up. But following the wave model, if it entered a more dense medium, light would slow down. So then they tested this out. They tested out to see whether light would speed up or slow down if it entered water. And what they found was that light slowed down when it entered water. And that was the breaking point. They were like, wow, the corpuscle model is trash. So they ended up picking the wave model instead of the corpuscle model. So yeah, now let's go through polarization. So the polarization of light refers to the direction of oscillation of its electric field. So if we look at this light over here, light is unpolarized. So it is oscillating in every possible direction, in infinite directions. So this is unpolarized light. And now it hits the polarizing filter and it now becomes plane polarized. So it hits the polarizing filter and it goes through that polarizing axis, and now it is polarized in one direction, in the vertical direction. So now it can only oscillate in that one direction. And so this is what we call when the waves become plane polarized. So this is how you would detail the process of polarization. And unpolarized light can oscillate in basically every plane, but polarized light is restricted to oscillating in one plane. So there are a couple calculations that you also need to be able to do when talking about polarization. So the polarization of unpolarized light. So if we have unpolarized light like this entering a polarizing filter and then leaving the polarized filter, this polarized light will have an intensity half that of this one. So this unpolarized light will have its intensity cut in half as it leaves the polarizing filter. So yeah. So we have the initial intensity of light. So this is the unpolarized light. This is the polarized light. And we can see that the polarized light has 0.5 the intensity of the unpolarized light. So it gets halved basically. And then we have the polarization of already polarized light. So this is the already polarized light, and this is the polarized light again. So it gets polarized again. So what happens is now we follow Malus's law, where I equals I naught cos squared theta. So a big place where a lot of people make mistakes is a lot of students forget to identify whether the polarization question they're going for is the polarization of unpolarized light or the polarization of already polarized light. So it's very important to read the question carefully to identify whether the light entering the filter is already polarized or whether it's unpolarized. A lot of people forget to check if it's unpolarized and end up using Malus's law and get it wrong. So yeah, that's something that's very important to keep in mind for. So what happens is this pre-polarized light enters the gap, and then its intensity gets reduced via cos squared theta until the final intensity leaving the gap looks like this, or leaving the filter is I. So that's Malus's law. So now we will do a question. So unpolarized light is passed through a polarizer so that it is now plane polarized in the vertical direction. As it leaves, it passes through a second polarizing filter. At what angle should the direction of polarization in the second filter be so that no light passes out? So let's take a look at this, right? So unpolarized light is initially coming out and it passes through a polarizer. So now the light leaving, the light in question is now plane polarized. And now it enters a second polarizing filter. So the incident light is now polarized. So we're going to be using Malus's law. And then the question asks, at what angle should the direction of polarization in the second filter be so that no light passes through? So they're trying to find what angle theta should be so that I is 0. So we'll lay out all our things, right? So I equals I naught cos squared theta. So we need to let I equal 0. So I naught cos squared theta has to equal 0 now. So we can divide through by I naught. So we get cos squared theta equals 0. And so theta will equal 90 degrees. So that's kind of how we do it. Theta, when theta is 90 degrees, or when the filter is perpendicular to the direction of polarization, then then like no light will pass through. So that's something that you need to remember. So if light is polarized in the horizontal direction now, so if it says the light is plane polarized in the horizontal direction, all we need is a polarizing filter that filters in the vertical direction to allow no light to pass through. So it has to be horizontal to the direction of polarization for no light to pass through. So yeah, now we'll do a quick recap on diffraction and interference. So diffraction is when waves bend around obstacles. So you can see this is when it bends around obstacles, and obviously the smaller the gap, the more it will bend around obstacles. So here it diffracts, and here it also diffracts. And interference. So constructive interference and destructive interference. That's what we need to know, or that's the two main things that we'll need to know for physics in module 7. So when waves meeting together, they collapse into a single wave. So if they're in phase, as in, you know, they both have the troughs and the crests at the same place. So if they're in phase, so you can see these two are in phase, they will undergo constructive interference. So they will add together, they will add together wave 1 plus wave 2 to form constructive interference. So it will increase, the amplitude will increase. So the waves are in phase, there's constructive interference. So these are also in red, so you need to be able to differentiate between constructive and destructive interference. So this is constructive interference. And then we have waves which are not in phase. So there's wave 1 and wave 2, which are not in phase. So this is what happens when they're not in phase. So you can see now, like the peak is, you know, at the bottom. Like they don't align properly. They're like perfectly one wavelength out of phase. And what happens when they're perfectly one wavelength out of phase is, or not one wavelength, half a wavelength out of phase is, what happens when they're perfectly half a wavelength out of phase is they form destructive interference. So destructive interference is where they complete destructive interference is when they completely block each other out, and wave 1 plus wave 2 ends up equaling just a straight line. So they completely block each other out. That's what happens. So the waves are out of phase, and so they completely block each other out. So yeah, now we'll go through Young's double slit experiment. So what he did was this double slit experiment proved that like light was exhibited wave behaviors, right? So what he did was he'd shown light through two gaps at these two slits, and he'd observe a diffraction pattern. So we can see here, right? These two slits are really close together. So basically almost less than a millimeter, right? And the screen is really far away from the slits, like around a meter. So what happens is we have a monochromatic wave, like a laser, for example. So the light from a laser, it enters or it hits this diffraction grating. So this line that we have here, we call this a diffraction grating. So it hits this diffraction grating, and what happens is, these gaps, it starts diffracting, right? It diffracts through these gaps, and now these two diffracted waves over here, they start interfering with one another. So yeah, we have a single source of light waves, and so the screen is really far away from the slits, like about a meter away. And what happens is, so we have each slit becomes a point source. So yeah, it starts diffracting through these slits, and so now each slit becomes a point source, and now we have two identical but independent sources of light. So because this light monochromatic source of light diffracts equally through both these slits, they each become 2 point sources. So now we have identical but independent sources of light. And what happens is these two sources of light, they start interfering with one another. So yeah, they have constructive and destructive interferences with one another, and you can see this is where the lines, they intersect with one another. So what happens is by interfering with one another, they produce an interference pattern of bright and dark spots. So we have the bright spots over here, like this, and then we have the dark spots like this. So they produce an interference pattern of bright and dark spots. And the screen really far away from the slits, like a meter away, will look something like this. So yeah, they'll undergo constructive and destructive interference. The constructive interference is these white spots over here, or the white bands, or the light bands, and the dark spots, or the dark bands, are formed by destructive interference, where the light cancels each other out, or almost cancels each other out to form the dark shadowy bits. So that's what Young's double slit experiment showed, or the observation of his experiment, and that kind of showed us that light can undergo diffraction and interference. So yeah, the interference pattern on the screen is caused by the different distances by the light to each point on the screen. So yeah, the same distance traveled, if they travel the same distance, so these 2 point sources, right? Just 1 point source, this is 2 point source. If they travel the same distance, they'll be in phase, and so they'll undergo constructive interference. So if we go back now, the midpoint over here, they'll travel the same distance to the midpoint, right? So if they travel the same distance to the midpoint, the two waves will be in phase, and so they'll undergo constructive interference to the greatest degree to form what we call this middle white band. We call that a central maxima. So that's what it will form. It will form the central maxima because these two travel the same distance to get to the middle, and so they'll exhibit constructive interference, and so they will produce a central maxima, or a very bright white band. And so yeah, will result in a bright spot on the screen. Now what happens if the interference pattern on the screen is caused by different distances traveled by light to each point on the screen? So if wave 2, so this wave over here, the red wave, if wave 2 travels an extra one wavelength, then the waves are still in phase because it's just one wavelength. So it's shifted like, one wavelength apart, but the troughs and the crests are still in phase. So what happens is it still undergoes constructive interference. So we still get a bright spot on the screen. So that's what these spots are. So we have the central maxima here, and then we have the first maxima, second maxima, etc. So these like other white spots, that's what they're caused by. When wave 2 or wave 1 travels an extra distance to get to the bright band or to the same distance, but they're still in phase. So that's what the other maximas are caused by. When they travel an extra something lambda to get to the spot, but they're still undergoing constructive interference. So they'll still produce a bright spot on the screen. Now we have what happens when when wave 2 travels an extra half a wavelength. So what happens when it travels a half a wavelength is now they're out of phase. So if they travel an extra half a wavelength, it looks like this. So it looks like this. And because it looks like this, they're now out of phase, so it will undergo destructive interference. So here, when they're out of phase, we'll get a dark spot on the screen, so they undergo destructive interference. So for example, central maxima here, we have the first minima. So these dark bands we call the minima, right? So this is the first minima, this is the first minima. So for the first minima, what happens is, so let's take this one for example, slit number 2 is closer to the first minima. So what happens is, slit 1 travels an extra half wavelength to get to the first minima than slit 1. So slit 2 travels an extra half wavelength to get to the first minima than slit 1. The other way around, sorry. Slit 1 travels an extra half wavelength to get to the first minima than slit 2. So this point source travels an extra half wavelength to get to the first minima than slit 2. So what happens is, now the waves, now this wave and this wave are now out of phase by half a wavelength. So it will end up looking like this. And so because of that, they'll undergo destructive interference and produce a dark band or a minima. So that's how that works. And that's how these dark bands or minimas are produced by destructive interference when they're something half wavelength out of phase. So they could be more than half a wavelength out of phase. So it works for 1.5 wavelengths out of phase, 2.5 wavelengths out of phase, etc. But if it's an integer value like this, if it's an integer value, then the troughs and the crests will be in the same place. So then it will undergo constructive interference. So yeah. We can now predict the location of the maxima. So, we can predict, like 1, 2, 3, 4, 5, the location of these maxima using the pattern shown below. So using this formula. So d sine theta equals m lambda. Explaining this, we have d is equal to the distance between the two slits. Theta is equal to the angle that from the center line. So if we go back now. So this is the first maxima, right? Theta would be the angle from the center line. So the angle that it would take to get up there. So that's theta. Lambda is obviously the wavelength of light. M is the order of the maxima. So the first maxima is found when m equals 1, and second maxima is found when n equals 2, and etc. It goes up like that. So first maxima is found when m equals 1, second maxima is found when m equals 2. This middle band, as I mentioned before, is called the central maxima. So yeah, that's how that works. So let's go to the question now. Calculate the angle from the central maximum to the third maxima if 900 nanometers of light is shown through 2 micrometer slits 4 millimeters apart. So first thing that we do is we need to make use of all the information that they've given us. So they've given us wavelength is equal to 900 nanometers, and they've given us the distance. So if we go back to D is the distance between the two slits. They've given us the distance between the two slits is 4 millimeters. So light is shown through 2 micrometer slits 4 millimeters apart. So that's what they've given us, right? So now we need to use the formula, rearrange the formula to calculate the angle. So we need to find theta. What we do is we have d sine theta equals to m lambda. M is equal to 3 because we're trying to find the angle between the central maximum to the third maxima. So we look back again. Third maxima is when m equals 3. So d sine theta equals m lambda. So now we rearrange it, right? So we do sine theta is equal to m lambda on d. Theta is equal to sine inverse of m lambda on d. So what's very important here is, and something that I would recommend as well is, I wouldn't recommend subbing all these values into the formula until you rearrange it to get your desired answer. So you can see over here, I didn't sub anything in. I rearranged the formula, so sine theta equals m lambda on d, and I got theta equals sine inverse of m lambda on d, and then I subbed in the value. So I got theta equals sine inverse m lambda on d, and then I subbed in the values. It just makes things easier that way, and it also makes things easier to write that way. So yeah, and then we would plug this into the calculator, and you should get 0.039 degrees of like angle or something close to that. And the important thing here is it's trying to show you how short or like how minimal these angles are. So the diffraction grading or like the diffraction pattern is very tiny. So the angle between the central maxima and the third maxima over here is 0.39 degrees. So it's very tiny, even tinier, 0.039 degrees. So it's incredibly tiny. So that is what it's trying to show. And just like how we found the maxima now, we can also find the minima. So instead of doing like just m, instead of doing an integer value of m, now we do an integer value of m plus a half. So we can see when it's a half out of phase, it becomes destructive interference. And when it's half a wavelength out of phase, it becomes destructive interference. And so what we do is we do m plus half lambda. So again, distance is the distance between two slits, or d is the distance between two slits, theta is the angle, lambda is the wavelength, and m is the order of the minima. So the first minima is found at half a wavelength. So you can do this a different way. You can do m minus half lambda or m plus half lambda. Doesn't really matter. What you need to know is that the first minima is at half a wavelength, the second minima is at 1.5 wavelength, etc. So yeah, now we can look at the resolution of diffraction patterns, and a way that the diffraction pattern, the resolution of it can be increased is by using like a greater diffraction grading or a diffraction grading with more slits. So if we look here, the double slit diffraction pattern for a single slit envelope is something that looks like this. So it's kind of chunky, kind of thick over here. For a 3-slit diffraction, it becomes thinner, right? So you can see more. So you can see more information over here. But the single slit envelope remains pretty similar. And now for a 5-slit diffraction, it's very detailed now. Like compared to the double slit diffraction in the single slit, it's very detailed. Or like compared to the double slit diffraction, the 5-slit diffraction is very detailed, right? So we can see all these little bumps and stuff. So yeah, the resolution or the detailing of the diffraction pattern improves greatly as your diffraction grading increases, or as the number of slits in your diffraction grading increases. So that's something you want to keep in mind as well. So now let's look at the features of the model. So light consists of small discrete energy packets called photons. So yeah, this is now us entering into the quantum model of light. So yeah, so we first got the particle model of light, and then we now went through the wave model of light, right? So we went through the wave model of light, and we found out, right? So the particle model and the wave model went head to head, and the wave model won, right? So the corpuscular model was now disregarded, and now science was focusing on the wave model. But after the wave model, we also got the quantum model. So let's look at the features of this quantum model. So this quantum model details that light is consisting of small discrete energy packets called photons. So you might have heard of photons before. You might have heard of it as photons are light particles and stuff. But yeah, they're discrete energy packets, and the quantum model of light describes light as being made of photons. And so the energy in each photon is related to the frequency of the light. So if the frequency of the light becomes greater, the packets of energy, these photons, the amount of energy that they carry in these packets also increases. And we'll go through the equation in a bit. And the intensity and amplitude of light waves is related to the number of photons. So light with a greater intensity will have a greater number of photons going through. And the photons are a fundamental particle, meaning they cannot be divided. Just like the protons neutrons, and electrons, they're fundamental particles. And this means that they have to be emitted or absorbed in full. So you can't absorb half a photon because they're a fundamental particle, which means you gotta, absorb the entire photon. So this is the all or nothing principle. So yeah, those are the features of the quantum model. The quantum model of light was now motivated by several failures of the wave model of classical physics. So we went from classical physics to now, quantum physics. So yeah, so the wave model now, we said that where the particle model and wave model claimed together and the wave model won. And the wave model now came across a couple problems as well. And these problems are what led to the photon model, coming out. So the couple of the issues that the wave model faced was the ultraviolet catastrophe and the photoelectric effect. So we'll go through both of these, right? So yeah, these are pretty prominent things. So you really need to be able to describe the ultraviolet catastrophe, or at least know how it affected our understanding of physics. Same with the photoelectric effect. The photoelectric effect, you will have to do calculations on that in module 7 as well. So we'll look at both of these and we'll explain how the wave model fails for both of them. So yeah, let's go through a black body first. So a black body is a perfect absorber and emitter of electromagnetic radiation. That's what the definition of a black body is, and you need to be able to define these. So nothing is reflected off of it. It is only absorbed, so light does not reflect, it is absorbed and then re-emitted. So yeah, and it's only theoretically existing, and stars are a good approximate of a black body because stars can absorb, so something that perfectly absorbs and perfectly emits, it only exists in theory. But stars are a good approximation of this black body. And what happens is these black bodies, they emit radiation across the electromagnetic spectrum. So we can graph these as a black body radiation curve. So that's also something that you need to look out for, a black body radiation curve. So this is what it looks like. So a black body radiation curve, so we can look at the x-axis and the y-axis, right? The x-axis has the wavelength of radiation. The y-axis has the intensity. And the units of this intensity are arbitrary. It's just, you don't need to worry about the units, but you need to worry that it's the intensity and the wavelength. So we can see here that, for something of a temperature, so we can see the link that we make between temperature and the actual graphs, right? So something with a temperature of 6,000 kelvins, it peaks at around, greenish yellow. So it peaks at around a color that's around greenish yellow. So that's how we link wavelength to temperature. We'll talk about this later. It follows something called Wien's law. But this is how we use a blackbody radiation curve. Or this is how a blackbody radiation curve will be tested in module 7. So yeah. So what is the ultraviolet catastrophe, right? So it links to the blackbody radiation curve. So scientists tried to use the wave model to predict the blackbody radiation curve using the wave model, right? And this is what the classical theory or wave model predicted. So they predicted as the wavelength decreased, the amount of energy, the frequency would keep increasing, right? So light had a fixed speed. So light of close to zero wavelength would have close to infinite frequency, right? So what would happen is it would keep increasing to infinity. Now, what's wrong with that? It violates the law of conservation of energy, right? Because you cannot have something with infinite intensity or infinite energy. It's just not possible. So that's the issue, and that's the ultraviolet catastrophe. It was a catastrophe because light couldn't, an EM wave couldn't carry infinite energy. That would violate the laws of conservation of energy, and so that was the issue. So yeah, the first problem was that. So the problem that I mentioned was that the classical theory predicted that light would increase exponentially and the frequency would approach infinity as light would approach, or the wavelength would approach zero, and so this violates the conservation of energy. The next thing is that if we go back here, so the blue, the red, and the green lines, this is what was observed from a theoretical black body. So this is what was observed. And as you can see here from the classical theory, it doesn't match. So that's another problem. So the classical theory didn't match the observed curves. And this failure became known as the ultraviolet catastrophe. So if you want to explain the ultraviolet catastrophe, you want to go through the two problems. And you might even want to draw a graph between, the observed value and the classical theory to show that, frequency approaches zero for the classical theory. So yeah. So what Max Planck did was, so Max Planck is pretty important as well. You'll know what Planck's constant is. So this is in the data sheet. So what Max Planck did was he came up with a mathematical trick to fix it. So what he did was he considered the radiation to be emitted in discrete packets called quanta. And this idea of discrete patterns or packets follows the idea of if we go back, like the quantum model of light. So we say the quantum model of light also carries energy in discrete energy packets called photons, similar to what Max Planck did to, fix the ultraviolet catastrophe. So what he did was, he said, or he used a mathematical trick. So in his ideology, Planck thought of Planck thought of what he did as a mathematical trick and not a true solution. So what he did was, he thought radiation, or he considered radiation to be emitted in discrete packets called quanta. So quanta of energy. So each energy of each quanta was attached to the frequency E equals HF. Now this formula is quite important. So E equals HF, what we do is, H is a constant. So H is the constant 6.626 times 10 to the power negative 4. F is frequency. So if we want to find the amount of energy that's carried in a photon, because it's also carried in discrete energy packets, we need to find the frequency of that light particle, or that wave, or that light. So if we find the frequency of light, then we can find the energy carried in that photon, or that discrete energy packet, following E equals HF. So that's that formula. So we have E equals mc squared, E equals HF as well. So E equals HF is quite an important formula that you'll come across quite often throughout your physics journey. So we'll revisit Planck's constant in module 8. So now let's go through Wien's law, which I mentioned a bit before. So what can we do with a black body curve? Surely we don't just learn a black body curve just so that we can say the classical theory didn't work. Well, we do actually have to do calculations with it. So I did mention before, the reason 6,000 Kelvin, 5,000 Kelvin, an object with 6,000 kelvins of temperature, if we go up now, we can see that the wavelength peaks at around yellow. So we could say it peaks at around yellow. So this object with 6,000 kelvins would appear yellow to us. That's kind of what it's trying to show. So if we go now to Wien's law, lambda max, or the max wavelength, the peak wavelength, so the peak wavelength is here, 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 and here for each respective wave. So the peak wavelength is equal to B, which is Wien's constant, over temperature in kelvins. So what we can do is, we can find the temperature of stuff like, stars, for example. We can find the temperature of stars by looking at the spectrum, finding their peak wavelength, or peak, wavelength of peak intensity. And then we can use that to do T equals B over lambda. And we can use that to find the temperature of those stars. So that's what Wien's law is. So yeah, we can see here, for an object with 2,500 Kelvin, the wavelength with maximum intensity is around 1.2 micrometers, etc. So yeah, now let's go through a question, Wien's law practice question. So this graph shows the electromagnetic radiation emitted from a black body cavity. So what is the best estimate of the temperature of this black body? So what would we do, right? So we have this formula, and we're trying to find temperature. So we do T equals B over lambda. So what we do is, first we write the formula, lambda max is equal to B on T, and then we try to find the max wavelength, right? We find an approximate. So if I draw the line from the max wavelength down here, we get approximately 490 nanometers. And now what I do is, so I have lambda max equals 490 times 10 to the power of negative 9 meters, and I do T is equal to B on lambda, which is equal to 2.898 times 10 to the power of negative 3 over 490 times 10 to the power of negative 9, which is equal to, if I now put this into the calculator, it should be equal to 5.914 times 10 to the power of 3, which is approximately equal to 5.9 times 10 to the power of 3 Kelvin, to two significant figures, and that gives us our answer of A. So that's how we would do it. All we're doing is rearranging the formula, and we're trying to find the peak wavelength. So our next, failure of the classical model of light, that is the photoelectric effect. So yeah, another unsolved problem of the 19th and 20th century was the photoelectric effect. So now let's look at the experimental setup here. So this is what the experimental setup looks like. So we have a vacuum chamber. We have, the electrons reaching the gap. So we have the gap, and then the electrons traveling, we have the metal surface over here, which the electrons eject through. So light strikes this metal, and what happens is electrons from this metal gets, sent outwards to the detector, or towards the gap. So electrons leave this metal to the gap, and they go through the ammeter, and we detect the current. So we detect the photo current, basically. So this is the setup for a photoelectric effect. It's in a vacuum, light strikes the metal, the electrons in this metal, because metals have free moving electrons, the electrons in this metal get ejected out of the metal into the detector, or the gap, and then it goes through the ammeter and the battery, and we can find out properties like the photo voltage or the photo current, etc. This is what the setup looks like. And basically what happened is current was detected by the ammeters, confirming that electrons were emitted. So that's what's very important here as well. And that, detection of current and electrons is what the photoelectric effect is. So when the photons strike the metal, electrons are emitted. So the photoelectric effect. So yeah. Expectation versus reality. This is a big, conflict that allowed us to, expand on our understanding of models, right? So the expectations by the wave model of light was that light of greater intensity emits higher energy electrons, right? That's what the wave model predicted. If we have a greater intensity of light, it would emit higher energy electrons. But what we found was, so the photo voltage wouldn't increase. So the photo voltage would kind of, dictate the energy of the electrons, right? What we found was that the photo voltage wouldn't increase. More often, the photo current increased. So as the intensity of light increased, the photo current increased. And photo current is kind of represented by, the number of, electrons that are moving through. Right, the number of electrons that are going through the circuit. That's what photocurrent is given by, instead of photovoltage, which is the energy of those electrons. So this indicated that as the intensity increased, the number of electrons emitted would also increase. And this kind of makes sense if we think about the photon model, right? Because the photon model stated that, if we go back all the way back to the photon model, the photon or the quantum model of light indicated that intensity is related to the number of photons. So a greater number of intensity would emit a greater number of photons. So that kind of makes sense, because if we now increase the intensity, right? If we increase the intensity here, we would be sending in more photons, right? And if each photon has to be absorbed, because photons are fundamental particles, so if each photon corresponds to one electron leaving, then this greater intensity of photons would cause a greater number of electrons to also be emitted, right? Because the intensity of light means more photons colliding, so more electrons leaving. So that kind of makes sense. So then the quantum model made sense for that. So the greater the intensity, the photocurrent would also increase. And then what another expectation was that exposing the metal to light for longer allows energy to build up in electrons until enough for the electron to escape. But in reality, that wasn't really, observed. In reality, what happened was, no matter, let's say this. So if we initially shine, light of intensity of 1, for example, arbitrary numbers. So let's say we shine electricity of 1, and no photoelectric effect was observed. The expectation was that if we shine this intensity of 1 for an hour, then some photo, or a period of time, then some photoelectric effect would be observed, but nothing was. That's because if we now think back to the quantum model of light again, right? Photons have to either be fully absorbed or not absorbed at all. So if the photon doesn't have enough energy to make the electron escape, then it won't be absorbed at all, right? So what happens is, there is no buildup of energy, because the photon collides with the metal. If it doesn't have enough energy, nothing happens. If it does have enough energy, then the electron leaves. So leaving the light on for a long enough time at a low enough energy level won't cause it to any electrons to be emitted, because all the photons colliding with the electrons won't have enough energy to make the electrons leave. So that kind of, if that makes sense, that's how the photon model of light explained this effect. So yeah, the wave model of light said that electricity or energy would build up. If we leave it at a low intensity, energy would eventually build up, causing the electrons to escape. But that wasn't observed. What was observed was that no matter how long we leave it at, if it's a low enough intensity, no photoelectric would be observed. And that kind of makes sense following the photon model, as I mentioned before, because if the photons don't have enough energy, then they're not going to be absorbed at all. So no electrons will feel the need to leave the metal. So that kind of makes sense. And the next one was that the energy of the emitted electrons will be dependent on the intensity of light. So very similar to the first one. As I mentioned before, again, it's not relevant. It's not. So that was one of the expectations, and the reality was the complete opposite, or not relevant at all, because the energy of the emitted electrons, the intensity of light only refers to the number of photons colliding, not the energy of those photons itself. So the energy of the emitted electrons depends on the energy of the photons, which is not dictated by the intensity of light. So the photon model of light, or the quantum model of light, basically explained everything. It basically explained all the observations, and the observations all contradicted the expectations. So the wave model was seen as very inaccurate because it couldn't explain most of everything that happened in regards to the photoelectric effect. But the quantum model, which Einstein came up with afterwards, did explain almost everything and basically everything. And so the quantum model was now accepted. So this is how Einstein's gigabrain was now used to change up physics. So yeah. Expectation versus reality. Light of great intensity emits high energy electrons. That's not the reality, because in reality, the greater intensity doesn't affect electron energy. It increases the current, the photocurrent, because it causes more electrons to be emitted, as I mentioned before, because greater intensity means more photons, so more electrons emitted. And then we have exposing the metal to light for longer allows energy to build up in electrons until enough for the electron to escape. So again, no, because the emission of electrons was always instantaneous from the moment light struck the metal. So by instantaneous, I mean the photon would collide. If it had enough energy, the electrons would instantaneously be emitted. If it didn't have enough energy, nothing would happen. And no matter how long those, so let's say the amount of energy for an electron to leave is 1. And the photon hits it with an energy of 0.5. So nothing would happen because it doesn't have enough energy, so it wouldn't be absorbed. No matter how long I keep hitting that electron with 0.5 energy photons, it won't leave. I have to hit it with an energy of 1 or greater for that electron to leave. So it doesn't matter if I leave it for longer. There is no build-up of energy. It either hits it and leaves or it doesn't, because now we're talking about discrete packets of energy. So either the discrete packet of energy is enough or it isn't. And then the next one is the energy of emitted electrons would be dependent on the intensity of light. And the reality is that the energy of emitted electrons was dependent on the frequency of light, because frequency dictates energy following E equals HF. So frequency dictates energy, not intensity. Intensity dictates the number of photons. So yeah, now let's explain the reality. So light hits a metal as photons. So they're carrying packets of energy followed by E equals HF. And the size of this energy packet is dependent on the light's frequency, again following this formula. Each electron absorbs this energy from one photon. So if that photon has enough energy, then it will absorb that energy. And then, a certain amount of energy is required to free it from the metal. So that's what I was talking about earlier, about 1 and 0.5. That's what I was talking about. So yeah, a certain amount of energy is required to free it from the metal. And each metal has its own, requirement of energy. So it's different for every metal. And the excess energy from the photon is converted into the electron's kinetic energy. So if the photon now has energy of 2, and the amount of energy required to free the electron is 1, the photon will hit the electron, and the electron will leave with a kinetic energy of 1, because 2 minus 1 is 1. Same with if the photon had an energy of 3. If it hits the electron with a requirement of 1, the electron will leave with a kinetic energy of 2. Now, if the photon had an energy of 1 and it hits an electron of 1, it will leave the metal, but at 0 velocity. So it will just leave the metal, but it won't travel anywhere, because it would leave the metal at a kinetic energy of 0, because 1 minus 1 is 0. So that's something you also want to keep in mind. So yeah, the excess energy from the photon is converted into the electron's kinetic energy. So yeah, so the photovoltage would increase as the amount of the excess energy from the photon increases. So yeah, so the kinetic energy of the emitted photoelectrons is dependent on the energy of the photon it absorbs and the amount of energy it takes to break the electron free. So we followed this formula, EK equals HF minus lambda, and we call lambda the work function, EK equals HF minus phi, and we call phi the work function of the metal. So the minimum frequency required to overcome the work function is HF equals phi, and this is called the threshold frequency. So yeah, that's a threshold frequency where F is equal to, that symbol over H. That's the threshold frequency. And the minimum frequency required would only cause, the minimum frequency required, if I take a photon and hit it with the minimum frequency required, the electron emitted would have 0 kinetic energy because it has no leftover energy, right? So yeah, that's what EK is, the kinetic energy of the electron emitted. So that's given by HF minus the work function. For questions, they'll often give you the work function of the metal, and they'll ask you to calculate the kinetic energy of the emitted photoelectron. They could also ask you to calculate the work function by giving you some other values, but overall, the equation itself is pretty self-explanatory and pretty simple. So yeah, now let's go through a couple of questions. So EK equals HF minus phi, or whatever the symbol is. Calculate the energy carried by a photon from light of frequency 300 gigahertz. So yeah, now we have light of frequency 300 gigahertz. We have the frequency, so we can calculate this. And we can calculate the energy carried by a photon. So we don't need to worry about work function right now. We only need to worry about the energy. So E equals HF. That's what we need to do. So yeah, E equals HF. We know what H is. It's on the data sheet. 6.626 times 10 to the power of negative 34 times 300 times 10 to the power of 9, which is equal to 1.9878 times 10 to the power of negative 22 joules. So yeah, E equals HF. That's kind of what the packets of energy look like. Next question. Calculate the wavelength of a photon that carries 3.976 times 10 to the negative 19 joules of energy. So this is what I mentioned by wavelength, right? So it doesn't really follow HF minus lambda again. It follows HF. So now we're trying to find the wavelength, right? What do we have when we look at this formula? We have E. E is equal to 3.976 times 10 to the power of negative 19 joules of energy. What else do we have? We have H. And now what is F? So if we look at, photon, right? Photon travels at the speed of light. C is equal to F lambda. F is equal to C on lambda, right? So we can now find lambda as well. So E is equal to HF, which is equal to HC on lambda following, this simplification. And now we can rearrange to find lambda. So lambda is equal to HC on E, which is equal to 6.626 times 10 to the power of negative 34 times 3 times 10 to the power of 8 following the speed of light over the amount of energy. So it's 3.976 times 10 to the power of negative 19. And this simplified is equal to 4.999 times 10 to the power of negative 9, which is approximately equal to 500 nanometers. So yeah, that is how we would calculate it. And if you look at the way I calculated it again, you can see that I rearranged all the algebraic terms to get me the answer before I subbed everything in. So I knew what lambda was equal to, and then I subbed everything in to make my life a lot easier, instead of subbing in the values in at the very beginning. So yeah. A beam of monochromatic light strikes a piece of aluminium in a vacuum chamber as shown in the diagram below. What does the frequency of this light need to be so that the current will flow in the circuit? The work function of aluminium is 6.54 times 10 to the power of negative 19 joules. So yeah, we need current to flow in the circuit, right? So what does the frequency of this light need to be? So we're trying to find the minimum, the threshold frequency basically. So we're trying to find HF. So we let HF equal to this value. So HF equals to 6.54 times 10 to the power of negative 19. We divide through by H to get F, and then we find the frequency of light. So F equals 6.54 times 10 to the power of negative 19 divided by 6.626 times 10 to the power of negative 34. So yeah, EK equals HF minus lambda, or minus 5, or whatever that symbol is. HF equals this symbol, or the work function of the metal. F is equal to the work function of the metal over H, which is equal to 6.54 times 10 to the power of negative 19 over 6.626 times 10 to the power of negative 34. And that gives us a value of 9.870208 times 10 to the power of 14, which is equal to approximately 9.9 times 10 to the power of 14 hertz, to two significant figures. So yeah. Now that we know what the photon model is, we can use it to study the properties of matter based on how it interacts with EM radiation. So we call this spectroscopy. So if we go back to the very beginning, if we go back to over here, spectroscopy. So spectral analysis. So this is what we're going to go through, spectral analysis. So we're very close to finishing spectral analysis, and then we have special relativity at the end. So we'll look at Einstein's mega giga brain at the very end. So yeah. Right now we're going through spectral analysis, which is trying to find out properties of our stars. So we look at stars and we're trying to find out its properties by studying its spectrum. So that's what we do, spectral analysis. And then we're going to go through special relativity, which is quite it's like a sub-branch of quantum physics. And in terms of spectral analysis, you'll go through more spectral analysis in Module 8. So in Module 8, you'll go through even more detailed version of spectral analysis, or you'll add on to your understanding of spectral analysis in Module 8. So yeah, going back to slide, I think it was 58. Yeah, what we call this is spectroscopy, studying the spectrum of the stars, or of EM radiation and how it interacts with EM radiation. So yeah, We can do two things now. We can detect the frequencies of radiation absorbed when light is shown through a substance, which is the absorption spectrum, so how much light it absorbs, or we can find the emission spectrum, which is how much it absorbs and then emits. So we excite the substance, and then we detect the frequencies of radiation emitted by the substance as it relaxes. So maybe in junior high school, or maybe if you guys do chemistry, you guys would have done the flame test. So this is kind of very similar to the flame test. We excite the substance, we excite the electrons. For example, in the flame test, we excite the valence shell electrons, and then we detect the frequencies of radiation emitted by the substance as it relaxes or goes back to the ground state. It's quite similar to the flame test. So yeah, this is what we call an emission spectrum. So we can see here, the emission spectrum is like, the opposite of the absorption spectrum. So the absorption spectrum has dark bands, which shows, the wavelengths of light that it absorbs. And the emission spectrum has, light bands, which shows the wavelengths of stuff that it releases or it emits. So yeah, the first thing that we can calculate using spectral analysis is temperature, which we've already discussed. So regarding temperature, what we can do is we find the peak of the radiation curve. So we find the peak, or the max wavelength, the wavelength with the maximum intensity, and then we can use that to indicate the temperature of the star. So we find the wavelength with the maximum intensity. We have lambda max is equal to b on t. We rearrange to find t equals b on lambda, and we can find the temperature. So we already did this with the Wien's law. The next thing that we can do is composition. We can find the chemical composition of stars. So if you think back to the flame test, maybe if you did chemistry, you would have learned that, each metal has its own unique flame color, right? This is because each chemical has its own, discrete amount of energy that it will use to get excited and then return back to its, relaxed state. So they all have discrete levels of energy. And so the wavelengths of the energy, which corresponds to then the frequency as well, and so the energy carried by the photons. So the amount of energy that each element will absorb is unique. So they'll all have unique spectral lines because, if the energy that they absorb is unique, then the frequency that is carried in these packets of energy will be unique. And so in return, the wavelength will also be unique. So they'll all have unique spectral lines. And so we can analyze the spectral lines of these stars to then find out what their chemical composition is. So we can find out if it's, majority helium, majority other chemicals, etc. So the chemical composition is also something that spectral analysis can tell us. Next one. We can also find out the translation velocity. So it's very similar to the Doppler effect. So by the translation velocity, so a star is turning, right? It's spinning. And from our side, so say it's spinning, or just say it's spinning in general. So one side of the star is moving closer to us, and the other side of the star is moving away from us, right? Because as it's spinning, one side is coming closer to us, the other side is going away from us as it's spinning like this. And so in that case, we observe the Doppler effect. So that is in relation to rotational velocity. So rotational velocity, so one side is coming closer to us, the other side is leaving us. So if you can see here, what happens is the spectrum, it starts broadening. So this is due to the Doppler effect as well. So one half of the star experiences the Doppler effect in rotational velocity. The other half experiences the stretching of the wavelength as it's moving away from us. So that one will become, so the spectrum from one side of the star is blue shifted, while the other side of the star, it's red shifted because one is moving closer to us, the other one is moving away from us, one half and the other half. So that's rotational velocity. In terms of translational velocity, that's where the entire star is moving. So if a star is moving closer to Earth, it becomes red shifted. It becomes blue shifted because the wavelengths become shorter. So if the star is moving close to us, the wavelengths become shorter. And this is what happens if it becomes blue shifted. So they retain, very similar bands that show the chemical composition, but as opposed to a stationary star, it's now blue shifted. And if the star is moving away from us, it becomes red shifted because the wavelengths get stretched out following the Doppler effect. So now it becomes red shifted. So that's kind of how you can see translation velocity and how you can see rotational velocity. So in this one, this is a normal spectrum, and if it's rotating, then the spectrum will broaden because one side is blue shifted, the other side is red shifted. So yeah, that's so far we know temperature, composition, translational velocity, and rotational velocity. Next, we can find density as well. So we have something called pressure broadening. So denser stars have more blurred spectral lines, and there's more uncertainty in the interactions between atoms and their energy changes as well. And we have what we call pressure broadening. So it broadens as well, but the difference between Rotational velocity and density is that we observe pressure broadening and it also becomes more blurry. So as opposed to rotational velocity where it broadens as well, but it's not that blurry, with density, the spectral lines start to blur as well. So we observe pressure broadening where it's also starting to blur as well. So that's how we can differentiate between density and rotational velocity. So yeah. Diagram 1, diagram 2, diagram 3. So we have, 3 different diagrams of similar stars, right? Similar star, or a similar chemical composition of these stars. And we have a couple different differences between these spectrums. So if we go here now, what we see here is one of them is shifted. So if you see here the lines, they have a similar pattern, right? So we can tell is one is shifted, and because of that, this star is so if we go back now to check, red shifted means it's moving. So this is stationary. Red shifted means it's moving to the right, moving towards the red spectrum. And if we look here, if it's shown through hydrogen, this is what it would look like if it was stationary. So diagram 1 shows us a stationary view of what's happening. So now let's go through the star Croesus. So diagram 2, right? What we can see here is the pattern of these bands is very similar. The pattern of these bands is same, but the whole entire pattern is shifted to the right. So this star is red shifted. So what we can tell by that is star Croesus, or I don't know how to pronounce it, but I'll just say Croesus. Star Croesus is moving away from us, or away from Earth. Now let's look at star Dromus. So star Dromus, if I connect these lines, you can see that it's slightly moving to the left. So you can see here that it has the same pattern, violet, blue, green, and red. So the chemical composition of both star Dromus, Croesus, and the source is, or like diagram 1, is the same. So star Croesus and star Dromus share the same things. But as opposed to star Croesus, the spectral lines are more shifted towards the left, so it's more blue shifted. So we can say star Dromus is moving towards us a little bit, while star Croesus is moving away from us. And then another important thing is the lines are quite blurry and they're also quite broad, right? So this is an example of pressure broadening. So it's broad, but it's also blurry. So we can see here the star Dromus is a lot more dense than star Croesus. So what I would do here to answer this question, right, if it's asking us to compare between star Croesus and star Dromus, I would have a couple subheadings. So the subheadings that I would initially do is, because I can't see anything about rotational velocity, I'd have one subheading called chemical composition, the next one called, translation velocity, and the next one called density. And under these 3 subheadings, I would explain their differences. So the chemical composition is the same because they share the same patterns. Their translation velocity is different because one's red shifted, one's blue shifted, and their density is also different because one has evident or visible pressure broadening and the other one doesn't really have that. So yeah, that's how you would explain this. Now we can move on to the final section, which is special relativity. So in 1905, Einstein proposed 2 postulates which have insanely strange results for time and space, right? So it is very trippy. So what he said was, the speed of light is an absolute constant and the same in all reference frames, all inertial frames of reference. And an inertial frames of reference is like a frame of reference where we're not accelerating, we're moving at a constant speed. So no matter what our speed is, as long as we're moving at a constant speed, to us, light will be moving at a constant speed, which is, approximately 3 times 10 to the power of 8. So that's pretty trippy, right? Because say we were moving at, so light, the speed of light is given by c, right? Say we were moving at 0.9 c. And as you know, nothing can travel faster than the speed of light, right? Because, if you watch time travel movies, if you travel faster than the speed of light, you go back in time or go into the future or stuff like that. So yeah, the speed of light is an absolute constant. It is also the maximum speed that you can achieve theoretically. So yeah, say we're traveling at 0.9 c, right? And we look to our left and we see light traveling. So you would think, because of relative velocity, that if we're traveling at 0.9 c and we look to a wave of light or a light beam, we'll see that light beam traveling at 0.1 c. That's what you'd think, right? But in reality, in our frame of reference, even though we're traveling at an inertial frame of reference at a speed of 0.9 c, from our perspective, we'll be looking at light traveling at 1 c as well. So relative velocity is kind of like broken here. So even though we're traveling at 0.9 c, we're looking at light and we see light traveling at 1 c. So light doesn't change its speed for us, which is very weird. And then the next thing he said was that all inertial frames of reference are equivalent, which is, pretty true, because if you think about the train question, right? So a train is traveling at a constant speed. if we throw a ball, right, that ball isn't going to like, fly back if we're traveling at a constant speed, right? It's just going to like, form that parabolic motion and bounce properly. Just like if we were standing stationary and we threw a ball, it's going to follow parabolic motion and land properly. If we were accelerating, then we're no longer in an inertial frame of reference. And so because we're accelerating now the ball is going to like probably fly back or fly forward. But if we're in an inertial frame of reference, then the physics in an inertial frame of reference are equivalent. So yeah, his first postulate, so these are Einstein's postulates. His first postulate was that light is an absolute constant and the same in all reference frames. So yeah, scientists were already starting to suspect this like, behavior from the experimental results where, it's very hard. They always, no matter how fast you go, light always appears at the same speed. And so yeah, it was already suspected, but this was Einstein's postulate. And the speed of light, c, is approximately equal to 3 times 10 to the power of 8 meters per second. And so yeah, we can say that all inertial frames of reference are equal as well. So yeah, as I mentioned before, by inertial we mean a non-accelerating, so a frame of reference where we move at a constant speed, at a constant velocity, or we're at rest. So yeah, inertial means non-accelerating and traveling at a constant velocity in this case. And yeah, if I'm in a room and unable to see the outside world, I wouldn't know if the room was at rest or moving at constant velocity. That's kind of what the inertial frame of reference is showing. So if we don't know, if we can't compare to another frame of reference, so we're only at our frame of reference, the only way we can tell if we're moving or not is if we start accelerating. If I'm traveling at like, infinite speed constantly, and I can't see the outside world, I'd never be able to tell if I was moving or not. And yeah, so what the reason for an inertial frame of reference is that all of Newton's laws hold up within an inertial frame of reference, regardless of what speed you're traveling at. So this is what was going back to the example with the ball, right? If you throw a ball, it would follow parabolic motion. If you're traveling at 500 meters per second constantly, same as if you're traveling at, 1 meter per second constantly. The ball would travel the same parabolic motion. And so that kind of shows that, the Newton's laws holds up in all inertial frames of references. So yeah, why does this become a big deal? So now think about the train thought experiment, right? So we have the light clock, right? And it goes to 1, so we have 1 tick in the light clock, which is the time taken for a beam of light to bounce back, 1 tick. So it goes up to the mirror and bounce back to the sensor, that's 1 tick. So now, let's look at a light in the clock, in a train, moving at a very high speed. We have the light clock in a train moving at a very high speed, right? So if I observe this from inside the train now, I see it going up, then down. So that's what I see if I'm in the train. So if I'm in the inertial frame of reference of the train, then I see the light going up, then down. So it looks straight, right? But now, if an observer is viewing that light from outside the train, what I see now is I see a triangle. So I see light, going down, but because the train is also moving down, I see it going diagonally. So if you look over here, in the rightmost picture, I see if I'm outside of the train, I see light traveling diagonally, and then I see light traveling up again. So why is this important, right? So this is what I see here: diagonally up, then diagonally down. If I'm in the train, I see this straight down, straight up. Why is this important? Well, if you think about it, this event and this event happen at the same time, right? It happens within the same time frame. And now if you think about it, the distance that light travels here in this event is greater than this, right? And it happened in the same time frame. So that means that, light travels faster here than it does here, which is very odd, right? So yeah, the observer outside the train sees light traveling a greater distance than the distance seen by the observer inside the train. Because if I'm outside the train, I see light traveling this entire distance, which is greater than if light just went straight down and straight up. So, I'm seeing light travel like, greater distance because I'm outside the train, as opposed to if I was inside the train. So, that's pretty trippy. So yeah, the speed and what makes it more trippy is that the speed of light needs to be a constant. This is following Einstein's postulate. So then if the speed is constant, but it's traveled a greater distance, then that means to compensate, the time taken for that to travel has been longer for a single tick in the light clock. So that means, in reality, the time taken for this to happen is longer. So it's like more time has passed for me than it has for the person inside the train. So technically, it's like a means of time travel. So more time has passed for me because I need to compensate for the greater distance I've seen because, light speed is constant, right? So I need to compensate for the greater distance I've seen. by experiencing this event in a longer time, even though technically it happened in the same time frame. Does that kind of make sense? So a longer time has been taken for me compared to the person inside the train, because the distance that he sees is less. So yeah, what happens is, because light travels a greater distance for me outside the train, a longer time is taken for me as well. So the tick takes longer for me as well, to allow for the speed of light to be constant. So this is what we call time dilation. Time passes more slowly for fast-moving reference frames. So yes, so as opposed to the guy inside the train, which doesn't need to see time traveling that fast because this distance that light travels is not that big, I've experienced a longer time. So time dilation is what happens. So the time passes more slowly for fast-moving reference frames. So T naught is proper time. So time in the reference frame at rest relative to the light clock. So T naught in this case is the time that the guy inside the train measures. So the time that it takes a light to go straight down and straight back up, that's T naught. T is the measured time, so the time measured by the observer. So T is the time that I measure for light to travel down and up, so that's T. And the velocity of the moving frame is the velocity relative to the observer. And to find the dilated time, we followed this formula, which is in your formula sheet. T equals T naught over root 1 minus V squared over C squared. So this formula is in your formula sheet, so you don't need to worry too much about it. So yeah. Similar to time dilation, we have length contraction. So length measurements become relative as well. So length contraction, so lengths are measured to be shorter for fast-moving reference frames. So if I see, a train 10 meters long traveling at close to the speed of light, that 10 meters will keep shrinking. So I'll see it at 3 meters maybe. So yeah, length, it gets contracted in the faster and faster we go to a person from an outside reference frame. If I was still in the train, I would see the train as 10 meters because relative to the train, I'm not moving because I'm in the train. But if I'm outside the train and I'm watching the train move, then it's shrunk to me. So yeah, it's like two different realities. It's pretty trippy. And the important thing here is you need to understand the frames of reference. If you understand the frames of reference and you're able to identify which frame of reference you're looking through, then you get basically every question correct. So L naught is proper length. So for my example, the proper length would be 10 meters because the train is 10 meters long. And L is the measured length by the observer outside that inertial frame of reference. So if I'm outside that frame of reference and I'm seeing the train move because I'm not in the train, then I will measure L, the measured length. If I'm in the train, then I will measure L naught, the proper length. So yeah. The hardest part of these types of questions is, deciding which is the relativistic quantity. So it's basically deciding which one is the correct frame of reference. That's the hardest part. So it's the hardest part is defining which one is LT and which one is L naught, T naught, because it's all relative, right? What's important to know here is there's no absolute frame of reference. There's no frame of reference where everyone can look at everything and see no time dilation. Every frame of reference is relative to another frame of reference. So yeah. If I'm measuring the length of a spaceship moving at 0.2 c, then my reference frame is relativistic because it's moving with respect to me. So I'm not at the rest frame. But if I'm inside the spaceship now, then my frame is the rest frame because I don't see the spaceship moving. I'm in the spaceship. I'm moving at the same speed the spaceship is moving. But if I'm at rest and I'm seeing the spaceship move at 0.2 c, then my reference frame is considered as relativistic for that problem right there. So yeah, let's do a couple questions now. A next-gen spacecraft developed by NASA has a rest length of 50 meters. This craft can reach speeds of 0.2 c. What would its length while traveling at the speed be measured by someone back on Earth? So yeah, for someone back on Earth, are they relativistic or are they in the rest frame? Well, the spaceship would be moving with respect to Earth, right? So if I'm on Earth, then I'm on the Earth's frame of reference, and from the Earth's frame of reference, the spaceship is moving. So I'm on the relativistic frame. So L naught in this case is 50 meters because it has a rest length of 50 meters. So L naught is 50 meters and we're trying to find L. So we're trying to use this equation. So we're trying to find L. So no, nothing tricky is going on here. L equals L naught root 1 minus V squared C squared. So if we look at V is 0.2. So we have everything we need. Now we can plug it in. So A, L equals L naught over 1 minus V squared C squared. We have L naught equals 50 meters, V equals 0.2 C. So now we plug it in. So L is equal to 50 square root 1 minus 0.2 C over C squared, which is equal to 50, square root 1 minus 0.2 squared, and that's equal to 48.989 meters, which is approximately equal to 49 meters, the two significant figures. So for someone back on Earth looking at the spaceship, it's shrunk by 1 meter. But for someone in the spaceship, it would be like, they would see it as 50 meters. So for someone on the craft, they're not moving with respect to the craft, right? So if I took a tape measure, if I'm in the craft and I take a tape measure and measure the entire thing, I'm not just going to find that it's shrunk by 1 meter. I'm not moving with respect to the spacecraft because I'm in the spacecraft. So I would measure it as 50 meters. So someone back on Earth would measure it as 49 meters. Someone on the craft would measure it as 50 meters. So that's how that relativistic length contraction works. So yeah. There are ways that we have proved these experiments long after Einstein's first formulated theory. So we have observed the change in lifetime of high-speed particles, so muons. So muons, they have a very short lifetime, and so scientists went up to a mountain and were like, we'll measure how many muons come from space downwards. And the expected value was like, let's say the accepted value was 5, right? They expected 5 muons over 5 minutes to, be sensed as it comes from space because it has a very short lifetime. But what happened was they saw a lot more than 5. And the reason for this was because the muons were traveling at relativistic speeds. So from the muons frame of reference, it has a lifetime of 5 minutes. But from the Earth's frame of reference, because the muon is moving at close to the speed of light, that time would be dilated, the time would be longer. So from the Earth's frame of reference, from the scientist's frame of reference, this muons had a half-life of 8 minutes. So it went from 5 minutes to 8 minutes. These are all example values, by the way, just to help you guys visualize what's happening. So from the muons frame of reference, they would only live for 5 minutes. But from the scientist's frame of reference, these particles, muons, would have a lifetime of 8 minutes. And so they'd be able to reach 8 minutes down into the Earth as opposed to 5 minutes. So that's why the expected value was a lot greater than the accepted value was a lot less than the observed value because they didn't expect muons to live that long. And that kind of proved that the time dilation existed. And then there were also atomic clock experiments where they tried to travel around the Earth multiple times to try and see if the time would change in the clocks, and it did. Some of the time in the clocks were behind the other ones, which showed that time dilation existed once again. And then there's also the fact that we try to accelerate things to be faster than the speed of light. So it's very important to realize that we can't actually accelerate things faster than the speed of light. No matter how hard we try, we can't, and that's because it links to the idea of energy. So no matter how hard we try to accelerate something at the speed of light, we can't because we need infinite energy. And that's called relativistic. It's related to relativistic mass, which is also relativistic momentum. So to achieve a momentum that allows us to reach the speed of light or go faster than the speed of light, we need more than infinite energy, because as we approach the speed of light, the amount of energy we need to supply for that object to reach the speed of light is infinity, which obviously violates the law of conservation of energy. And then we also have the relativistic Doppler effect. So that's how we supported and proved Einstein's theory of special relativity. So going through muon decay. So these are the real values of muon decay. So muons are tiny particles produced in space. And they're produced around 10,000 or 10 kilometers above the Earth. Yeah, 10 kilometers above the Earth. Average decay for muons are 2.2 times 10 to the negative 6 seconds. So yeah, not 5 minutes, very tiny. They die pretty quickly. And so muons, they travel at 98% the speed of light. So they're at relativistic speeds. They travel very fast. And the distance it travels before decay in non-relativistic circumstances is, we can find the distance now, 0.98 times 3 times 10 to the power of 8, that's the speed, times 2.2 times 10 to the power of negative 6. So in non-relativistic circumstances, they travel 646.8 meters, which would reach nowhere near the surface of the Earth 10 kilometers away. But scientists found them close to Earth's surface thanks to special relativity because, from our frame of reference, something moving at 98% of the speed of light would experience time dilation. And so that 2.2 times 10 to the negative 6 seconds would become greater and greater as it gets closer and closer to the speed of light. And so because that time becomes dilated, because that time becomes greater, this value, this time, would become greater, so that this this distance that it travels before decay would also increase, and that's due to special relativity, if that makes sense. And so muon decay was one of the experimental evidences that showed the existence, or that proved or supported Einstein's theory of special relativity. Yeah. From the perspective of an observer on Earth, the time taken for a muon to decay is dilated. The proper time of decay is taken from the frame of reference at rest relative to the muon. So what's the lifetime of a muon moving from Earth's perspective? So to find this, right, to find the answer to this question, what you would do is you dilate this value, 2.2 times 10 to the negative 6 seconds. So we go back to the formula, right? T naught. Proper time is the time in reference frame at rest relative to the person moving. So with respect to the muon, because the muon isn't moving with respect to itself, so in the frame of the muon, it has a half-life of 2.2 times 10 to the negative 6. So this becomes proper time. So proper time, T naught, is 2.2 times 10 to the negative 6. What we're trying to find is measured time. So measured time we do is equal to T naught divided by root 1 minus V, which is 0.98 c, so 0.98 c squared over c squared, and then we would get measured time, and then we would use that measured time t to multiply it by this value, and after doing that we would get an answer much greater than 646.8 meters. It would be a lot greater because we'd find them close to Earth's surface. So yeah. Now a couple questions about special relativity as well. A radioactive particle has a half-life of 2.5 microseconds while it rests in a laboratory. So this becomes our proper time because it is at rest in a laboratory. So yeah, when we're measuring it with respect to itself, when we're measuring it within its own inertial frame of reference, it has a half-life of 2.5 microseconds. The same particle is accelerated to a high speed by a particle accelerator, increasing its half-life to 10 microseconds. How fast was it traveling relative to the observer? So if you go back to the formula, measured time is now 10 microseconds. Proper time is 2.5 microseconds. And the question is asking us to find v, velocity. So going back now, what we'd do is we'd first lay it out. So we have T naught is equal to 2.5 times 10 to the negative 6 seconds. T is equal to 10 times 10 to the negative 6 seconds. And we have the formula here. So we'd write down the formula and we'd write down the values that we know. Next, what we'd do is we'd rearrange the formula. So T naught over T on T naught is equal to, so what I did was I multiplied both sides by this value and then I divided through. So I multiplied, then I divided to get T naught over T is equal to root 1 minus V squared over C squared. Because the end game here is we need to rearrange this equation to make V the subject. So there's a little bit of algebra here. Then I squared both sides to get 1 minus V squared over C squared is equal to T naught over T squared. Then I rearranged to get V squared is equal to C squared in brackets 1 minus T naught over T squared. So what I did was I moved this entire thing to the right, I moved this entire thing to the left, and then I multiplied both by C squared. And then I rearranged, so I square rooted both sides to get V equals square root C squared in brackets 1 minus T naught over T squared. And then what I did is subbed in the values. So I subbed in the values here, and then it gave me an answer of 2.904 ... times 10 to the 8 meters per second, which is approximately equal to 2.9 times 10 to the 8 meters per second. So yeah, very close to the speed of light. Hence why the time here increased by a factor of 4. So yeah, now we can go on to relativistic momentum. So this is why. So this explains how we can't accelerate things to go faster than the speed of light. That's due to relativistic momentum or relativistic mass, which is what I think they used to call it in the old syllabus. So yeah, this is the concept of relativistic momentum, which is the concept of momentum adjusted for the effects of special relativity. So instead of mass, we have relativistic mass. So mass also changes with respect to the velocity that we travel at. So we just, plug that into the idea of momentum and we get this equation. So P is equal to P naught over, or M naught V over root 1 minus V squared over C squared. And this entire equation now imposes a limit on velocity. So we look over here, Newtonian physics, so P equals mv, it shows that at C, we should have a momentum magnitude of mc, right? But so it follows a straight line, and following Newtonian physics, it doesn't seem too hard to achieve a speed of light or a speed of c. But following the observed values and also relativistic momentum, we see that as our speed approaches c, the momentum required approaches infinity. And so the energy required to supply an object with this momentum also approaches infinity. And so that shows that we have a limit on velocity. We can never reach the speed of light following our current understanding of physics, because we need to supply an object with infinite energy, which violates the laws of conservation of energy. So yeah, that's how that shows that we haven't, that's what happens when we impose a limit on velocity. And this is a formula that's also on your formula sheet, and it's very similar. We need to find the rest values and then the measured values. That's the only thing that makes these equations hard. So to get good at these equations, what I would suggest is really I'm underlining the questions. So oftentimes in your questions, they won't be very direct by saying at rest in the laboratory. They'll be, it'll just say it has a half-life of 2.5 seconds, cut this out, and then it'll say its half-life was increased to 10 microseconds. So some people will mess it up by saying 10 is equal to T0 and 2.5 is equal to T, as opposed to the other way around. So you really got to read it and understand what the question is asking of you, and then that will help you to understand which one is the rest and which one is the relativistic values. So yeah, so special relativity is quite a tricky concept to get your head around, and it's okay if it doesn't make sense now, because it's quite hard, because you need to think a lot about your perspectives, your frames of reference, etc. You can watch this video over here or search up simple relativity to help you out with it. And yeah, think of yourself as Einstein, and then try stepping through the logic of that thought experiment. So if math helps you understand things, you can try deriving the formulas for time dilation. So yeah, if you want to derive the formulas, you can do that. For deriving the formulas, you need to go back to the train question, and you need to find the difference in lengths and times. And if you let them equate, you can try and derive it. But yeah, going back, yeah. If math helps you understand things, you can try to derive formulas for time dilation and length contraction, and try and argue different, or try and discuss different scenarios with friends. So, and this helps you think about how things how the relativistic equations work. So yeah, if you try and this is something that actually helped me. If I discussing examples with friends actually helped me wrap my head around the different perspectives and different frames of reference that I have to look through to actually get questions right. So yeah, and what's important is to always go back to this thought experiment. So this thought experiment here, this is something that's very important. So this thought experiment, you need to be able to possibly even explain this very well. So you need to possibly be able to even draw these diagrams pretty well, because some questions that could have come up in your exam is to probably detail Einstein's thought experiment, because it's quite a famous thought experiment and it's a part of your syllabus as well. So yeah, there's a couple different things now. So if we go back now, yeah, now we can talk about the mass energy equivalent. So if we go back to the very beginning, in slide number 7, we're now on to Einstein's energy mass equivalent. So we're pretty close to the end. So if we go back now, Einstein's mass energy equivalent. So now we're finally getting to E equals mc squared. So we've probably seen this formula. You might even know what this means. And basically what it means is the energy contained in one particle is proportional to its mass. So yeah, so mass is basically energy. Or mass is equivalent to energy. That's what Einstein's mass energy equivalence formula is. Mass is equivalent to energy, and energy is equivalent to mass. So mass stores energy, and energy is released when mass, when mass releases, or energy is stored in mass, and mass stores energy. So yeah, 1 kilogram of mass basically contains 9 billion joules of energy. So yeah, it contains heaps of energy. And the implication of this will then be later explored in module 8. We can talk about, the combustion of stars and stuff, and how much energy stars release. So yeah. Quick question now. How much mass will be required to generate 1 kilojoule of electrical energy? And assume that the mass can be converted to energy with 5% efficiency. So we need to look back to the equation E equals mc squared. What do they want us to do? So they give us 1 kilojoule. So they gave us E, and they want to find the mass that can be used to convert to energy with 5% efficiency. So they want to find the mass that can be used to generate 1 kilojoule of energy. So we're trying to rearrange this equation to find mass. So we have E equals mc squared. We rearrange this, right? So m is equal to E over c squared. But we have m times 0.05 because of this 5% efficiency equals E equals c squared. E over c squared, which is equal to 1,000 joules over 3 times 10 to the 8 all squared. And then m is equal to 1000 over 3 times 10 to the 8 squared, and that should give you your answer. So yeah, going back now. Any questions that you want to ask, feel free to ask in the live chat. And going back now to something that I find that is very important. Let me just quickly go over this. Go over this. Yeah, quick summary of everything that we've learned so far. So yeah, development of the model of light. So yeah, the model of light, you need to be able to know historical and modern models of light. So historical is like, Galileo, which is the 2 mountains, or Roma, which is the Io, Jupiter's moon. Fitzo and Foucault, which are the rotating mirrors and the rotating cogwheels. You learn a bit about Foucault in school. And modern means, which are like, oscilloscopes, lasers, and, superimposition of light waves. And then also wave behavior, such as diffraction, refraction, and interference, especially. And also polarization as well. Polarization is pretty important as well. Blackbody radiation, you need to know the implications of blackbody radiation, how that led to the catastrophe, the ultraviolet catastrophe. So, the blackbody radiation, how that didn't align with the classical model. So the classical model said that light would, if I go back over here, the classical model said that light would approach infinite intensity as the wavelength approaches 0. So, yeah, as wavelength approaches 0, the classical model said that, the intensity of light would approach infinity. That obviously violated the law of conservation of energy. And also, the experimental and observed blackbody radiation curves didn't align with the classical theory, and so that led to the ultraviolet catastrophe, which was then fixed or rectified by Max Planck. So it's like a little story, right? So we have the ultraviolet catastrophe. It was rectified by Max Planck, who said that energy was packed in discrete quantas, or discrete packets of energy called quantas. And so this, like that equation of E equals HF following Max, the constant, that energy is also then was then used by Einstein again in the photon model of light. And the photon model of light over here, the photon model of light. The photon model of light over here, that was very important as well, because it could explain the photoelectric effect, and it could also explain a lot of other stuff like, the ultraviolet catastrophe as well. It could fix the ultraviolet catastrophe because it followed Max Planck's use of discrete energy packets by taking that they were photons. So another thing that you need to memorize is all the ways that the photoelectric effect wasn't able, how that all violated the laws of classical physics. So the photoelectric effect, right? How the wave model wasn't able to explain the photoelectric effect. So you need to be able to know that the difference in intensity, and how so these 3 things basically: the intensity, that's very important, and how light would build up, and how that would cause electrons to be emitted, how that wasn't observed, that was false as well, and how the energy of emitted electrons would be dependent on the intensity of light. So this over here is very important. And the explanation over here is also quite important. In terms of the questions, yeah, so EK equals HF minus phi, or whatever the symbol is, that's also something to remember. And as I mentioned before, they can ask you to calculate the work function. They can also ask you to graph things. So they can ask you to graph this, and by graphing it, they can ask you to find the work function, as the work function would be, like the y-intercept basically. So yeah, they'll give you frequency, they'll give you kinetic energy emitted, and then they'll ask you to graph it, right? So if they ask you to graph it, frequency would go on the x-axis, EK, or the kinetic energy emitted, will go on the y-axis. The gradient of that straight line would be h. So the gradient would be Planck's constant. And they can ask you, questions can also ask you to find the Planck's constant by graphing E and F. So in that sense, this E will be y, h will be m, f will be x, and this will be c. So y equals mx minus c. So it's very simple. F will be the x-axis, so h will be the gradient. So if they give you kinetic energy and frequency and they ask you to graph it, then h will be the gradient. So if the question is asking for Max Planck's constant, make sure you graph the line properly, because the gradient will be Planck's constant, and the y-intercept of that line will be the work function of the metal, and each metal has its own separate work function. That's also something to remember. Yep, other than that, we have spectroscopy. So the 5 things to remember is temperature, composition, chemical composition, translational velocity, rotational velocity, and the density. You'll learn a bit more in Module 8 about other stuff. And then, yeah, Einstein's gigabrain postulates about the speed of light being an absolute constant and inertial frames of reference. Yep, the train thought experiment. So yeah, you're gonna make sure that the train is like, to supplement the longer distance that it travels, the time that it's taken to travel is also the same, is also greater. So yeah, you need to know the 2 postulates about light being always constant and inertial frames of reference being equal. This, as I mentioned before, should memorize this one. Yep, other than that, these formulas are pretty evident. These are all in the data sheet, so you don't need to memorize them. All you need to know in these experiments is you need to be able to identify which is the rest frame, or which is proper time, and which is measured time. And we went through a couple examples that should help you identify which is proper time and which is rest time. And yeah, other than that, also relativistic momentum is quite important. And that just shows that the main important thing about relativistic momentum is that it imposes a limit on velocity, and it shows us that c is basically the limit. The speed of light is the limit, because at that point we need to supply infinite energy, which we can't do. So yeah, other than that, we have the mass equivalence thing, which isn't too prominent in Module 7, because we'll go through more of it in Module 8. And that brings us to the end of the lecture. So yeah, thank you very much for sitting through this lecture. And if you have any questions, make sure to type it in the live question box, and also in the Q&A. If you want to type it in the Q&A, the 8 Notes Q&A, I'm sure that current students and past students just like me will answer it as well. But yeah, feel free to type it in the live Q&A right here, and I'll answer your questions for you. But yeah, other than that, thank you so much for listening to this lecture.